Hello, and welcome to Chapter 12, an introduction to the analysis of variance. In this first video, we'll discuss when you would use an ANOVA instead of a t-test. So for the past few weeks, we've been doing t-tests. We did a t-test for one sample, comparing the sample to the population. We did a t-test for independent measures, comparing two different samples to each other. And then last week, we did the t-test for repeated measures, taking one sample, but that measure is repeated. And for all of those, we just had two simple measurements we were comparing. So a t-test is used to evaluate differences between two treatments. It uses sample data to draw conclusions about populations, because again, we said we don't always have information about the population, so we take that sample data to draw these conclusions. Now the problem is that sometimes we have experiments where we have to do more than one hypothesis test. So if we do more than one hypothesis test, we're increasing our experiment-wise alpha. So each time we do a t-test, we have that type 1 error, or that test-wise alpha, okay? So each time we do that hypothesis test, we have this possibility of that type 1 error, that false positive. If we do multiple t-tests, we're increasing the amount of type 1 error we're making. So when we do an ANOVA, we can use an ANOVA when we only have two treatment means, but typically it's used in more complex situations where you have to do multiple hypothesis tests. So it's typically used to evaluate mean differences between two or more treatments. So t-test, we had two different samples. We had one sample that had measurements repeated 2 times, maybe before and after a treatment, or we have one sample and we're comparing it to the population. In analysis of variance, we can compare mean differences between 2 or more treatments. So one group of people that go through 3 different conditions, or you have 3 different groups of individuals. It's still using sample data to draw conclusions about the populations, but the test-wise and experiment-wise alpha are similar. So each hypothesis test you do gives you a type 1 error. When you do multiple t-tests, that adds up. When you do an analysis of variance, there are ways that the statistics control for that, and so your individual hypothesis test and your experiment-wise type 1 error are the same. So ANOVA evaluates all mean differences simultaneously with one test, regardless of the number of means. So it avoids the inflated experiment-wise alpha. It's just my little meme, a series of t-tests instead of an ANOVA. Yes, that clearly won't increase the risk of a type 1 error. So typical situations for using an ANOVA, it gives you a clear advantage over a t-test when you are comparing more than 2 treatments at the same time. For example, you have population 1, 2, and 3, each undergoing different treatments. You don't know the information about the population, so you pull a sample from that and you test that sample. You pull a sample from population 2, and you pull a sample from population 3, and now we want to compare these means in one test so we don't increase the experiment-wise. So just to go over some terminology, this word factor, and I believe we've had this before, but the word factor is the independent or quasi-independent variable. So it's that independent variable, and we call it a factor, that designates the groups that are being compared. So here we have one factor with 3 different levels of treatment. So one factor is the intervention, okay? So for my example here, I'm just going to go over a project that I was on when I was in college, and it was called Project Primer. And we basically had 3 groups of subjects. One group got no intervention, a second group got 3 interventions, and a third group got 16 interventions. And what this intervention was we went out into the homes of families that were part of a Head Start program. And they had older siblings that were in this Head Start program, and then they had younger children at home. And we went out to the families, and we brought books and games and songs to learn some sort of concept. And so again, and they got cognitive scores before and after the intervention. And so we had one group that didn't get any intervention. They just had their cognitive scores measured through a variety of different tests. We had a second group that they had 3 interventions. They had one at the beginning of the school year, one in the middle, and then one at the end. And then a third group that got 16 interventions. So 16 times throughout the year, we would go out to the families, we would read a book, there'd be some concepts such as colors. We would have a game that would also be associated around the idea of colors, and then we would have a song that also would have something to do with colors. And then we would encourage the family to continue with those activities on a daily basis until we came out the next time with another set of materials for them. So the factor was the intervention with 3 levels. And again, I want to compare treatment 1 with treatment 3, treatment 1 with treatment 2, and treatment 2 with treatment 3. Sure, I could do t-tests for all those different comparisons, but then I'm increasing that experiment-wise error. So with the factor, I had one factor. I had one independent variable, and it has 3 different types of manipulations or levels. So the levels are the individual conditions or values that make up a factor. So I had 3 levels. 1, no intervention. 2, 3 interventions. And 3, 16 interventions. So to continue on with terminology, K denotes the levels. So a lowercase k tells me how many levels. It's the individual conditions or values that make up a factor. So for the Project Primer example, I had one factor with 3 levels, so k would equal 3. In a factorial design, as a study that combines 2 or more factors, and we'll get into that in a couple of weeks. So in this chapter, we will only consider single factor designs, so designs that have one independent variable with 2 or more levels.